Now let's talk about another important concept called reciprocal lattice. As the name suggests, I'm going to take some reciprocal. Okay. Now, but what is reciprocal lattice? How do I obtain it and what is its significance? So reciprocal lattice is going to be very useful to understand the energy band diagrams in semiconductors. It's just easier to deal with the reciprocal lattice. That's why we do that. Okay. So reciprocal lattice, it's kind of a transform. Have you heard of Fourier transform? Fourier transform? How many of you have heard Fourier transform? Can you raise your hands? Fourier transform or Fourier series? Okay. So when we talk about, say, transform, what we are doing, we are representing the same information in a different way. It's the same information, no information is lost, but the way of representing the same information is a little bit different. Okay. So reciprocal lattice is also similar. It's kind of a Fourier transform of the real lattice. So no information of the real lattice will be lost, but we are just representing the same information in a different way. Why we are doing that? Because that's going to be easier for us to deal with later on when we talk about the energy band diagrams. Okay. So it's a Fourier transform of the real lattice. Real lattice is the lattice which we have been talking about till now. Reciprocal lattice is the Fourier transform of that. What's the exact meaning of Fourier transform? We'll see that. And it's obviously it's useful in understanding the energy band diagram. Also crystal diffraction, if you talk about X-ray diffraction, for example. So that can also be easily understood through the reciprocal lattice. So let's consider a simple example of 1D lattice. Simplest one. So how does a 1D lattice look like? Something like this. So this is a one-dimensional lattice and the primitive vector is A, or you can say the periodicity is A here, right? Now let's assume that there is a physical quantity which has the same period, right? So let's there be a function f of x which has the same periodicity as this 1D crystal. And what could that function be? It can be any physical quantity. For example, in reality, if you have actually some atoms placed on these lattice positions, these atoms will have some Coulombic potential around them, right? They have positive charge inside their core, right? There are electrons, but let's say the potential of electrons I'm neglecting. Say they have these ionic cores. Every atom has, say, some single positive charge, plus q, plus q, plus q, plus q. Okay. Now this plus q charge is going to create some potential around this, around its vicinity. Yes. How does that potential look like? Some 1/4 pi epsilon q by r, something like that, right? Inversely proportional to 1 by r. So if you move away from the atom, it's going to reduce inverse as the position. So something like this. If I have a positive charge and let's say this is the position, how will it look like? Something like this. Say this is a okay. So as you come closer to this, the potential energy becomes more and more negative. Okay. So this is an attractive potential well. As you move away from it, the influence will become lower and lower. Okay. So say this is V, it's going to be inversely proportional to R, mod of V. Right. Now if I have several such atoms placed together, how will the combined potential look like? Can you imagine? So one potential well looks like this, say around this. Now I have several of them. So what will be the total potential? You simply take the algebraic sum of the potential because of every atom. It's a scalar quantity, so you can simply superimpose them, take the algebraic sum. So how will it look like? if there is a potential like this because of every atom, and there are several of them together sitting near to each other, a distance apart, how will it look like? Something like this. Okay? If you combine them all together, you need to simply take the sum of all of these. Right? Now, what is this? This is the crystal potential. We say this is a crystal potential. Okay? So this is the potential that an electron is going to see if it is going to move in this crystal. And is it a periodic function or not? It's a periodic function. What's the periodicity? A. It's periodic with the same period A. So I'm talking about a physical quantity like this. Right? So let's say there is a physical quantity f of x, which can be potential or some other quantity, and it is periodic with the lattice. Now, because it's a periodic function, it has some period. What's the period? Period is A. It repeats after every A. So there is a concept of Fourier series. Whenever you have a periodic function, you can represent it as an algebraic sum of several plane waves. Okay? What do I mean by a plane wave? How do I mathematically represent a plane wave? When I say a plane wave, what does come to your mind? Some sine or cosine, right? Some sinusoidal or cosine, right? We can combine both of them and also say that this e to the power iota gx, g is some constant, this represent a plane wave, right? What is this? E to the power iota g is cos of gx plus some iota sine of gx. So if you want to represent only through, say, the real function, so that is cos x, but in general we can also say that this also represent a plane wave, right? It has this periodic part, but it's a complex number, e to the power iota gx. So that represents a plane wave. Plane wave means something which is oscillating. Okay? The theorem is that if this fx is periodic, you can represent it as the summation of several of these plane waves, and every plane wave will have its own g, right? So what is g? Actually, g is called wave vector of the plane. It is basically 2 pi by lambda. Okay? If you don't talk about, say, in e to the power iota gx, say it is simply cos of gx. So this g is 2 pi by lambda. Lambda is the wavelength, right, of the wave. Or in this case, it will be 2 pi by a because it's repeating after every a. Okay, but this g can be different for every wave. Okay, there are several waves of different wavelengths, and you are taking algebraic sum of the those waves. So how do you take the algebraic sum? You have e to the power g1x, e to the power iota g2x, e to the power iota g3x, and so on. And let's multiply them with some constant, say some c1, c2, c3, and now let's take the sum of these. So this is going to be your f of x. Now where will this series end? You can keep continuing this to, say, infinity. So you can start from something, and it can continue. Infinite number of plane waves. Now this c1, c2, c3, some of the waves, so depending upon what kind of function you have, some of the waves will have larger values of c1, c2, c3. So we will say that most of the significance of the function lies in those components. They are all different components, right? Some of them may have small values of c1, C2, C3 or whatever, right? So then we will say these components are not that important. The idea is that you represent this f of x like this, right? I mean, I can combinedly write that thing as this summation m cm e to the power iota gmx, and m can vary from minus infinity to infinity. Okay, and m is an integer, so it will be some c1, c2, c3, c4, c of minus 1, c of minus 2, however you want to index it, right? It's going to go from either 0 to infinity, you can say, or minus infinity to infinity, whatever way you like. It's going to be integer. So this is the Fourier series. You can always do that with any periodic function. People who are familiar with this, I mean, it's a simple thing. Who are not familiar, so it's a concept in the mathematics. You can always do this. Now, what is this reciprocal lattice? It's related to this thing. That's why we are studying all of this. Okay. Now, because fx is a periodic function, so what's going to happen? F of x plus a will be equal to f of x. I can write it like this because it repeats after every a. So f of x plus a is going to be equal to f of x, right? Now let me write the series form of this and equate it to the series form of this, and let's see what happens. Okay, so f of x is equals to summation of cm into e to the power iota gm x, right? And let me replace that x by x plus a. So what do? This is going to be cm into e to the power iota gm x plus a. Let me take this e to the power iota gm into a separate, and now I have this factor and this factor, and what will be the corresponding series of this? Cm into e to the power iota gm into x, right? On the left hand side it is this, on the right hand side it is this. Now left hand side has to be equal to right hand side for all possible m. I mean, you run m from say minus infinity to infinity, and you sum it up here, they must be equal. This can only happen when this term is equal to 1. If this term is equal to 1, then left hand side becomes equal to the right hand side, correct? So we can conclude that e to the power iota gma is equal to 1. Yes? If e to the power iota of any number is equals to 1, what will be this thing? This has to be integral multiple of what? Okay, when can this quantity be equal to 1? Give me some examples. So okay, let me put some values here of gm times a. This is going to be some number. What can this quantity be so that it gives me 1? E to the power iota, if this is 0, it's going to be 1, right? What else? E to the power iota of 2 pi. What is it? Cos 2 pi plus iota sine 2 pi. What does it give you? Cos 2 pi is equals to 1. Sine 2 pi is 0. So that gives me 1. Okay. E to the power iota 4 pi. E to the power iota 4 pi. What is it? Cos 4 pi plus iota sine 4 pi. Sine 4 pi 0, cos 4 pi 1. So any integral multiple of 2 pi, I can do minus also, minus 2 pi, minus 4 pi. Any integral multiple of 2 pi, e to the power iota, any integral multiple of 2 pi is always going to give me equal to 1. So this gm times a has to be an integral multiple of 2 pi. Okay, so what will be the gm then? Gm will be equal to 2 pi m by a, and where m is an integer. Okay, so what will be the values of the gm then? I mean, this is an integer. You can start it from minus infinity, goes through 0, go to plus infinity, right? So let's say m equal to 0, m equal to say plus minus 1, that will give you plus minus 2 pi by a, m equal to plus minus 2, that will give you plus minus 4 pi by a, plus minus 6 pi by a, and so on, right? Okay. Now this is what my GM is. So when you are expanding the fx in terms of these waves, e to the power iota gmx, now those gm, the wave vectors, have this form. They have to be equal to 0, plus minus 2 pi by a, plus minus 4 pi by a. And this is the information of the fx. Okay, where is the information of this f of x? So f of x can be expanded like this. So information of f of x is contained in this cm and in this gm. If you know the gm and the cm, you know the fx, correct? So no information will be lost if I have this gm and this cm. If I know them, I will do this summation, I will be able to obtain the f of x, right? So gm contains some part of that information. The set of all the points of gm is basically the reciprocal lattice. Now let me make another fictitious geometrical lattice and let me put all of these points in an array. How will I arrange these points? So there is a 0, and then let me put 2 pi by a minus 2 pi by a, 4 pi by a minus 4 pi by a, and let me arrange all of these points. So how will they look like? Something like this, right? 0, and this will be 2 pi by a minus 2 pi by a, 4 pi by a minus 4 pi by a, and so on. I can have another set of points which I can get from this GM. This new set of point is called reciprocal lattice. Okay, what's the lattice constant of this? What is the primitive vector of this reciprocal lattice? What's the distance between them?
A.
Not a. So this is 0, 2 pi by a, 4 pi by a, 6 pi by a. So what's the distance between them? 2 pi by a. Okay. So from the real lattice, I have created another lattice which has the same information, but it has a different primitive vector. What's the primitive vector? 2 pi by the magnitude of original vector. Right? What was the lattice constant in the 1D lattice? A. In the reciprocal lattice, it will be 2 pi by a. Okay? So it's another lattice. You are representing the same information differently. Right? So primitive vector is vector b, let me call it vector b, equal to 2 pi by a x cap, because it's a 1D. And why the reciprocal? Because you have taken the reciprocal of the original lattice constant, right? So that's why it's called reciprocal lattice. Is any information lost? No. I mean, of course, I can also calculate this CM through some procedure, but this GM represents basically the same information that I had here in a different way. Now, is this a real lattice? No. It's a geometrical representation, mathematical lattice, not a real lattice. Yeah, we can represent this as points, but it's not a physical lattice. It's just a mathematical construction. Any confusion in this? Okay. So this is the 1D. Let's take example of 2D. So reciprocal lattice for 2D rectangular real lattice. So my original lattice is rectangular, not 1D. It's in 2D. Looks like this. I have two primitive vectors, vector A1 and A2. A1 is A1x cap and A2 is A2y cap. You can obtain the reciprocal lattice of this real lattice by taking the reciprocals of their respective directions. So if this is say A1, so corresponding to this B1 vector will be 2 pi by A1 into x cap, and corresponding to this it will be 2 pi by A2 into y cap. Okay, it's a simple way to generate the reciprocal lattice in 2D. We can actually prove this. I'm not going to go to the proof, although I have given it in the slides. You may go through if you want, but for this course we just need to understand some basic concepts, so I'm not gonna go into the details, mathematical details of that. So any vector in the real lattice can be represented as this: r equal to n1 a1 plus n2 a2, right? I mean, n1 and n2 are integers, you know that, right? The position vector of any of the lattice points, right? Similarly, I can generate a reciprocal lattice which has the primitive vectors b1 equal to 2 pi by a1 x cap, corresponding to this 2 pi by a2 y cap, right? And you may notice that this is longer, this is shorter, this is shorter, this is longer, because you are taking the reciprocals. Okay, so this will be shortened, this will be elongated. Okay, and what will be the reciprocal vector? Like I have in the real lattice vector r, I can have another vector corresponding to this in the reciprocal lattice. I mean, it's a lattice, right? In a lattice, you can represent any point in the form of integral multiple of these primitive vectors, right? So what will be the reciprocal lattice vector? So some g equal to gm equal to m1 b1 plus m2 b2, where m1 and m2 are integers. So the position of any of this, any of these points can be represented by another vector which is called reciprocal lattice vector, given by m1 b1 plus m2 b2. m1 and m2 are integers. After all, I mean, reciprocal lattice is also a lattice, so it has all those properties as you have in a real lattice. It's just that its lattice constant is different. Okay, how do I relate this Rn and Gm? In the 1D, this Rn was basically some Na, right? I mean, this wasn't there, some n times a. Okay, and we saw that Gm into a is equals to some 2 pi into integer, right? A similar relationship we can also have here. So in general, you can write e to the power iota gm dot r is equals to 1. So this holds true. As we had this in 1D, we also have this in 2D. It can be proved, but I'm not going to do that. So you may go through the proof in the slides. For all m and n. M and n are integers. Okay, m means m1 and m2, n means n1 and n2. This, you take the dot product of this and do the e to the power of this, so you will always get 1. Always. How do I calculate the reciprocal lattice for 3D? Say I have 3D orthorhombic lattice. Orthorhombic lattice means it is it's a 3D version of the rectangular. It means A, B and C are not equal. They are perpendicular to each other, but they may have different dimensions, right? So this can be A1, A2, A3. So they are not all equal. So it's called orthorhombic, not a cubic. Cubic means A1, A2 and A3 are equal. Orthorhombic means they can be different, but they are mutually perpendicular. So let me have a lattice like this. Now the corresponding reciprocal lattice will be constructed similar to the 2D case. So this will become 2 pi by A1, 2 pi by A2, 2 pi by A3. Okay. So because this is the longest one, this will become the shortest one. Then this and this. So these are short. So this will become longer and this will become a little smaller than this. Because this is the shortest, this becomes the longest. Then this, and then this is the longest. So this becomes the shortest. Right, 2 pi by A1, 2 pi by A2, 2 pi by A3. Simple, but you can only do this when you have these orthorhombic, rectangular, cubic, these type of systems. It means A1, A2, A3 are mutually perpendicular to each other. You can then simply take 2 pi by a1, 2 pi by a2, 2 pi by a3. If they are not mutually perpendicular to each other, say they are at some angle which can be there, okay, then we can't use this method. Then we will have to use another generic method we'll talk about. Again, so this is Rn. Any point in the real lattice space can be represented as Rn, n1a1, n2a2 plus n3a3. Similarly, any point in the reciprocal lattice can be represented through a reciprocal lattice vector, which is gm equal to m1b1 plus m2b2 plus m3b3. And what will be the relationship between them? The same. E to the power iota gm, vector gm dot product vector Rn must be equal to 1. Or in other words, you can say this is basically 2 pi times some integer. Vector gm dot Rn, it has to be equal to 2 pi times some integer. So the next 2 slides are just going to give the proof of this. I'm going to skip that. You may go through on your own if you are interested. Some mathematics there. If you understand all of this, fine. You don't, we are not going to make use of it in our course. So we will only be concerned about the results. Okay. Yeah, one thing I forgot to tell you. So if you have a lattice which is Brillouin lattice, the original lattice is say Brillouin lattice, the real lattice. Then reciprocal lattice will also be Brillouin lattice. So this is also true. If original lattice is Brillouin, reciprocal will also be Brillouin. It can be proven. Again, you can go through these this mathematics. You will be able to understand that. Okay, what if we do not have a1, a2 and a3 mutually perpendicular to each other? So then what do we do? For that, we have some formulas that we can use. Okay, I again won't derive them, but we are simply going to make use of these. So if a1, a2 and a3 are not perpendicular to each other, the general relations are this. So you have b1 will be equal to not just 2 pi by a, but you have a1 dot a2 cross a3 here, and in the numerator you have the same thing, a2 cross a3. Okay, so in a way, see, what does this denominator represent, by the way? Volume. Yeah, we talked about it. If you have a1, a2 and a3, they are not say perpendicular to each other. I mean, they can be at any angle with respect to each other. So then vector a1 dot a2 cross a3, that gives you the volume of the parallelly pipe formed by these a1, a2 and a3. It's the same thing, the volume of that thing. And a2 cross a3 is what? It's an area, kind of. Right? If you take the vector product of 2 vectors, that gives you basically the area formed by those vectors. Right? So area divided by volume. You see that dimensionally b1 is still 2 pi by some length. See that? So the numerator is area, denominator is volume. Area by volume, it gives you 2 pi by some kind of a length. Right? So dimensionally it is still 2 pi divided by some kind of a length. It's a different matter that it's not 2 pi by simply a1 now. Similarly b2, so when you have b1, so correspondingly a1 you put here and the 2 other you put here and here. If you have b2, corresponding to this you put a2 in the denominator and the other 2, a3 and a1, you put here. Okay? And similarly b3, a3 and then this, a1 and a2. And the order of these matter. So a2 cross a3 is not equal to a3 cross a2. You need to be careful about that. It will be minus of that if you reverse the order. Okay, so to remember this, you can simply put them like this. 1, 2, 3. Okay, so for 1, you go like this, 2 to 3. For 2, you go 3 to 1. For 3, you go 1 to 2. Got it? For 1, 2 to 3. 2, 3 to 1. And then for 1, 1 we have already discussed. For 3, 1 to 2. So 1 comes before, then 2. Anti-clockwise basically. So in the orthogonal and rectangular case, we saw that B1 and A1 were parallel, B2 and A2 were parallel, B3 and A3 were parallel to each other. Okay, so A1 and say B2, if I say that if I take the case of say rectangular lattice, so they are mutually perpendicular to each other, correct? So if I take the dot product of them, that will be 0. Yes, because A1 and B1 are parallel, A2 and B2 are parallel, A3 and B3 are parallel. They are all mutually perpendicular to each other. They are all mutually perpendicular to each other. So if I have A1 dot B1, so that will give me some number. But if I do A1 dot B2, that will give me 0. Dot product of mutually perpendicular vectors will be 0. Okay. Similarly, if I do say A1 and B3, that will give me 0. So that relationship that we saw in the rectangular lattice or orthorhombic lattice, that holds true in general. So what do we have here is this. So if I have AI dot Bj, if I and j are equal, then that will give me 2 pi. If I and j are not equal, that will give me 0. You can check actually through this formula. Okay, if A and B have the same index, gives us 2 pi, different index gives us 0. That can be represented through this Kronecker delta function. Must have seen that previously. So delta ij means, so when I and j are equal, it is 1. I and j are not equal, it is 0. That's called Kronecker delta function. Okay, so in general, you can represent it as 2 pi into delta of ij. And this holds true, we all already know this. So how we came up with these formulas, we kept in mind these two definitions. And the form of these B1, B2 and B3 is that such that it will always satisfy this and this. In fact, I have given examples. You can in fact check that you want to do that. So A1 into B1, if I do say this vector A1 dot B1, if I do, so what is A1? A1 is simply A1. And what is B1? B1 is this whole thing, right? So 2 pi times this, and A1 is going to be A1 dot this whole thing. Numerator and denominator can cancel each other, so this will be equal to 2 pi. Simple, right? Similarly, you can test this, say A1 dot B2 or A2 dot B1. That will give you 0, right? Because if you do A2 dot product of A3 cross A1, that's going to be 0. Why? Why this term will be equal to 0? Can you tell me? A2 cross A3 dot A2, that is 0. Okay, what's the direction of A2 cross A3? So A2 cross A3 it's a cross product, and cross product gives you a vector, right? A2 cross A3 is going to give you a vector, but what will be the direction of that vector? Perpendicular to the plane which contains A2 and A3. So if I have, say, this A2 and A3, say this is A3, this is A2. Cross product is going to be like this. So this is A2 cross A3. Cross product vector will always be perpendicular to both A3 and A2. Got it? Now, if it is perpendicular to A2 as well as A3, so what will be the dot product of A2 and this vector? There is a 90-degree angle here, 0. Okay, so that's why A2 dot B1 is equals to 0. No, you can check more cases. A3 dot B1. It's all given here. You can try that. You can also try this property, right? I mean, B1 is also a reciprocal lattice vector. Yes. I mean, B1 is also a GM, right? GM is equals to N1 this M1 B1 plus M2 B2 and plus M3 B3. If say M2 and M3 are 0 and M1 is equals to 1, so one of the case will be G equal to B. So B is also a reciprocal lattice vector. So it should also satisfy all the properties that the reciprocal lattice vector does. So B1 dot any Rn, B1 dot any Rn must also be 2 pi times some integer. You can try that. It will be equal to 2 pi times n1. So b1 dot a1, what that will give you? That will give you basically 2 pi, right? b1 dot a1, because 1 and 1, so that gives you 2 pi times integer n1. b1 dot a2 gives you 0, b1 dot a3 gives you 0, so that is 2 pi times n1, right? So that property that gm dot rn, where gm is any reciprocal lattice vector, in this case that gm is equals to b1, that property is also fulfilled. You can try with B2, B3, whatever you want. Okay, now let's try to calculate the reciprocal lattice of some actual cases which we are going to use. What kind of lattice we will deal with? We are going to deal with silicon mainly. Yes. What kind of lattice structure does silicon have? Diamond structure. Yes. Diamond is composed of what? 2 FCC lattices. It's like a FCC, but there are some inside atoms. Okay. So we'll have to talk about what would be the reciprocal lattice of, say, an FCC lattice. What will be the reciprocal lattice of a, say, BCC lattice? Okay, let's see that. So let's talk about the reciprocal lattice of a body-centered lattice. What were the primitive vectors of a body-centered lattice? You can go back and check the notes. We talked about this in the last class, right? You basically sit at a corner atom and look in 3 directions. So in a body-centered lattice, you will have a center atom. So if I am sitting at a corner and I am looking at the center atom of some neighboring unit cells, so one this, one that, this, that. So these 3 will give me primitive vectors. We saw that, right? And you can actually represent them into in this form, right? You can easily calculate it, but okay, let me give it to you. A1 is this, A2 is this, A3 is this. Now what will be B1, B2 and B3? Can you calculate that? Try. What will be the B1, B2 and B3? Use those formulas, try to calculate. What is B1? B1 is 2 pi A1 dot what? A2 cross A3, and the same goes in the numerator. Now you have to calculate A2 cross A3 and then take the dot product here. Not very difficult. So how do you take the cross product of 2 vectors? You know, you have 2 methods, so you can do it like this: x, y, z. Whenever you have x, x, y, y, z, z, x cross x, y cross y, z cross z, that will be 0. But x cross y, that gives you z, y cross z gives you x, z cross x gives you again this. Okay, so anti-clockwise. X cross y gives you z, and you can do similarly. So if I do this and this, what do you get? a by 2 x cap minus y cap plus z cap cross a by 2 x cap plus y cap minus z cap. So this will be a square by 4. You can take these things out. X 0 x y, right? What does that give you? X cross y gives you z minus z, right? X z. I mean, you can do all of these things. So no big deal. Yeah. Either you can do this or you can use that determinant method, right? You must have seen that x, y, z, and you can put 1, minus 1, 1 here, then 1, 1, minus 1 here. So coefficient of these three, you put in these 3 rows, right? Take the determinant. So this into this minus this into this, then with a minus sign, and then you can also use the determinant method, whatever method you like. So eventually what you get is, you can try this example. You get this a square by 2 into y cap plus z cap by the a2 cross a3. And if you take the dot product with the a1, you can do that. So you get simply a cube by 2. A scalar number. So what will be the b1? b1 will be a2 cross a3, which is this thing, divided by this thing, which is v, basically a cube by 2. So it gives you this 2 pi by a into y cap plus z cap. Okay. Similarly, you can calculate b2, b3. Now, interestingly, now this b1, b2 and b3, look at these primitive vectors. Do they look familiar? So y cap plus z cap, right? It's like the center of a face. Yes. X cap plus z cap, center of a face. X cap plus y cap, center of a face. If you go back and check the notes, actually these are nothing but the primitive vectors of a face-centered lattice. If you check the face-centered lattice primitive vectors, you will find this, this and this. These constants might be different, but this, and this part will be the same. Okay, so it's a reciprocal lattice. Its reciprocal lattice is going to be FCC. If you have a BCC lattice, in the reciprocal space, you will have FCC. Why? Because the primitive vectors of the reciprocal lattice look like these, which are the primitive vectors of an FCC. Check the notes, you will find that FCC has the same form. Okay, so this is BCC, primitive vector, that gives you FCC. So here you have this primitive cell, which is formed by these 3 vectors in the BCC. Correspondingly, the primitive cell in reciprocal space will be this b1, b2, b3, parallelly piped, right? b1, b2, b3 are given by these things. So BCC lattice forms an FCC lattice in the reciprocal space. What do you expect? If I have FCC lattice, what will it form? It will form actually BCC. You can again prove that. That's on the next page. You can again simply take, say, A1, A2 and A3. And what is the form of A1, A2 and A3? If the real lattice is FCC, primitive vectors are A by 2 y cap plus z cap, A by 2 x cap plus z cap, and A by 2 x cap plus y cap. So these are the centers of these the three faces. This face, this face, this face. That gives you this. Now you use the same formula, calculate b1, b2 and b3. You will find that it's going to give you b1 is this, b2 is this, b3 is this. Now go back and check. A1 and A2 and A3 I mentioned for BCC, they are very similar. This part and this part is exactly the same. Okay. So this has the form of BCC. FCC gives you a reciprocal lattice BCC of lattice constant 4 pi by a. Okay. So for silicon, if I represent the silicon real lattice in reciprocal space, it's gonna give me a body centered lattice in the reciprocal space. Got it? I think there is a mistake here. In the calculation, it should be a cube by 4 here. Right? So that will make it 2 pi by a, 2 pi by a, 2 pi by a. This is correct. Correct this thing. Okay, so till now we have talked about what's a reciprocal lattice, primitive vectors of the reciprocal lattice. Seen 2 examples. Another important concept is called Brillouin zone. Again, why we are studying it will be very helpful in understanding the energy band diagrams. So what is a Brillouin zone? Brillouin zone is actually Wigner seed cell. We know how a Wigner seed cell look like, right? Wigner seed cell is a primitive cell, but a special kind of primitive cell. What you do, you sit at one of the lattice point, you look around, you connect with the neighbors, right? Take these perpendicular lines and the area or the volume captured by these perpendicular lines or the planes, they are Wigner seed cell. We know how to form them. Okay. Brillouin zone is, now Brillouin zones can be several special zones in the reciprocal lattice. So Wigner seed cell of the reciprocal lattice is called first Brillouin zone. Okay, so the difference is that I'm not making the Wigner seed cell in the real lattice, I'm making it in the reciprocal lattice. Reciprocal lattice is also a lattice, so the procedure to make a Wigner seed cell remains the same. Yeah. So if you have, let's stay here. So if you have a real lattice like this, right, reciprocal lattice will be this. A1 will become B1 2 pi by A1, A2 will become B2 2 pi by A2. It's a simple rectangular lattice, so you can simply take the reciprocals 2 pi by A. Now, the Wigner seed cell of this reciprocal lattice will look something like this. You have this lattice point. What I will do, these are the neighbors, this. I'm just going to take this, take the perpendicular, and this region that is formed, it is my Wigner seed cell, but it's a Wigner seed cell in the reciprocal lattice, and this is called first Brillouin zone. Okay. Now these things, these perpendicular lines, or in 3D they will be planes, so they are called Bragg planes. It's coming from diffraction theory and all, the name, but just a nomenclature. So they are called Bragg planes. Similarly, you can, so this is the first Brillouin zone. So first Brillouin zone, it's some kind of a region in the reciprocal lattice, right? If there is a first Brillouin zone, there can be higher Brillouin zones also, although they will not be as relevant to us. Will be mostly talking about first Brillouin zone, maybe second Brillouin zone or something like that. But there can be higher Brillouin zones also. So what's the definition of higher Brillouin zone? So say you have this reciprocal lattice and you create this first Brillouin zone by taking these perpendicular bisectors, and this is your first Brillouin zone. Okay. Now, how do I make a second Brillouin zone? So what you do, you have already looked at these neighbors. So they are nearest neighbors. In this rectangular lattice, they are nearest neighbors, and you have already taken this perpendicular. But then there are neighbors like this, and this. I can repeat the same thing. What I can do, I can take the perpendicular here, join them, take perpendicular here, right? Perpendicular bisector, perpendicular bisector. So I can make 4 more perpendicular bisector. Let's do that. So they will look like this. Now they are creating more regions. Now what is the second Brillouin zone? By definition, it's the region which you can enter from the first Brillouin zone by crossing only one Bragg plane. So I'm sitting here, and second Brillouin zone is a region in which I can enter by crossing only one Bragg plane. And where am I crossing from? From the first Brillouin zone. So what is that region? Now, if I look at this region, this is a Bragg plane. Yes. If I want to enter from here to here, I'm only crossing one Bragg plane. But if I want to enter, say, this region, I have to cross one Bragg plane, two Bragg planes. So this part is not the second Brillouin zone. If I am, say, entering here, so if I go from here to here, I am crossing 1, 2 and 3 Bragg planes, not the second Brillouin zone. So only this part, this part, this part, this part will be the second Brillouin zone. Okay, simple geometrical construction. What about the third Brillouin zone or any higher Brillouin zone? The third Brillouin zone follows the same definition. It's the region of the reciprocal lattice in which you can enter from the second Brillouin zone by crossing only one Bragg plane. So if I want to go from here to here in this region, I only cross this. But if I want to go from, say, here to here, 1, 2, 2 Bragg planes I will have to cross. So this is not the third Brillouin zone. This, right, there will be a region like this. So that will be the third Brillouin zone. Before we go to the third Brillouin zone, we will have to do the same. We will have to make more perpendicular bisectors. So I have already connected this and this, right? Let's go to even higher neighbors. So we have covered all of these neighbors. Now let me join this and this. That will give me this perpendicular bisector. This and this will give me this. This and this will give me this, and this and this will give me this. So one more set will be this and this. Okay, you keep going to the higher Brillouin zones, you keep making more and more perpendicular bisectors, more Bragg planes, so that you have more clarity. So from here to here, if I want to go, I only cross this one. So this region is the third Brillouin zone. But what about this region? If I go from here to here, I want to cross this and this. So 2 Bragg planes I am crossing. So not a valid third Brillouin zone. Okay. So this region, right? This region are all third Brillouin zones. Similarly, you can construct higher and higher Brillouin zones. Right. So this is the second Brillouin zone, set of all the points that can be reached from the second zone by crossing only one Bragg plane. Similarly, nth Brillouin zone will be set of points you can reach from n-1th zone by crossing only one Bragg plane. One important property of the Brillouin zone is that the total area of any Brillouin zone is equal. Area or volume. In 3D it will be volume. It means this area and combined area of all of these two, or the combined area of all of these three, they will all be equal. The geometrical construction is like that, they are always equal. Okay, this area, and if you say these 4, of course if you combine these 4, this is going to make a square, you know, the area will be equal. And if you take the area of all of these things, that will also be equal to the area of this. So these are higher Brillouin zones, although we will mostly be talking about the first Brillouin zone in this course. Now let's talk about what is the first Brillouin zone of FCC and BCC. Yes, we have already seen how a Wigner seed cell looks like for FCC and BCC. We saw that in the last class, right? And Wigner seed cell is the Brillouin zone, first Brillouin zone. The only difference is that it is in the reciprocal space. Okay, so if I have, say, a BCC lattice, what will be the corresponding lattice, reciprocal lattice, FCC. So the Wigner seed cell of the FCC will be my first Brillouin zone. Similarly, if I start with say FCC, in the reciprocal state, I have BCC, and Wigner seed cell of the BCC will be my first Brillouin zone. So how will they look like? For BCC real lattice, FCC is the reciprocal lattice, and for FCC you can construct the Wigner seed cell like this. We saw that in the last class, right? And for FCC real lattice, for example silicon, BCC Wigner seed cell will be there, right? I mean, it will be a BCC reciprocal set space, and you construct this Wigner seed cell. How does it look like? Look like this, right? So because it's BCC, so you have a point here, this, you know, and if you combine this and this, so this is that perpendicular plane. If you combine this and this is that perpendicular plane, right? The volume enclosed by all of these perpendicular planes is your Wigner seed cell, which is the first Brillouin zone. This is going to be very, very important in our course because it's related to silicon. The first Brillouin zone of the silicon looks like this. So I will revisit this, but when I will talk about the energy band diagrams. Okay. So we have been constructing the basis for what has to come next. So what we want to know the physics of the solids, basically semiconductors, in particular of semiconductors, right? For that we need certain tools. So one of the tool is the crystal information, right? Crystal lattice, how do we classify that, Miller indices, you know, Brillouin zones, reciprocal lattice. So we have captured all of that. The other important part that we need to understand is the quantum mechanics. Okay, so I'm going to give you some basic introduction of the quantum mechanics. It will take this class, probably the next class as well. Without that, we can't reach the energy band diagram. Energy band diagrams, they are coming from the quantum mechanics. So let's just review. Some of you might be familiar with the quantum mechanics. For some of you, it might be a totally new thing. But even if you don't know anything about the quantum mechanics, I'm going to cover some basics so you will get some idea what I'm going to talk about. Okay, so let's close this thing.